I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is Simpson's paradox. What does this mean? Well, it's not disbelief about Bart Simpson and Lisa Simpson coming from the same household. Instead, we'll be looking at the dangers of combining average values together. In class, I usually start with a puzzle. Person 1 has a 3.25 grade average in the fall and a 4.0 in the spring. Person 2 has a 3.0 in the fall and a 3.6 in the spring. Who has a higher GPA for the year? Other than the suspicion that if the obvious answer was correct, I wouldn't ask it, is there any reason to doubt that person 1 has the higher GPA? Consider the following possibility. Person 1 has an A and 3 Bs in the fall, an A in the spring. Person 2 has a B in the fall, 3 A's, 2 B's in the spring. Those fit the averages I told you, but overall person 1 has a 3.4 and person 2 has a 3.5. It sounds like a paradox. Person 1 has a better average in both semesters, but person 2 has the better average for the year. How did this happen? Well, as one of my students once said, I cheated by having the number of courses in each semester vary considerably. Person 1's 4.0 only came from one course, so the overall average is highly affected by the fall 3.25. Person 2's 3.0 only came from one course, so the overall average is more heavily based on the spring 3.6. Well, here's a real-life example. 2 treatments for kidney stones are compared. Treatment A works better for small stones. Treatment A works better for large stones, but treatment B is better overall. After the grade average example, I hope that you see that the statement is incomplete. You need to know how many data points are involved before you try to average the averages. Here are the numbers. Treatment A, 81 out of 87 for small, 192 out of 263 for large. Treatment B, 87% for small is less than treatment A. 69% for large stones is less than treatment A. Overall, treatment A, 78%, treatment B, 83%. The effectiveness of both treatments is significantly higher for small stones. Most of B's data came from small ones, so its average is higher than A's, for which most of the data came from the harder-to-treat large stones. Should we conclude that A is actually better? Well, 2 possible problems prevent this. Are the 87 and the 80 sample sizes large enough to place faith in A's average as being higher? Were there biases in how the treatments were chosen? For example, maybe doctors used B for the more difficult cases. You can also look at Simpson's paradox from the perspective of correlations. Correlation is a measure of linear trends in 2 variable data. If variable y tends to increase when variable x increases, then x and y are positively correlated. If y tends to go down when x goes up, then x and y are negatively correlated. Now suppose you have data in 2 categories, say small and large. If x and y are positively correlated for small data, and x and y are positively correlated for large data, don't x and y have to be positively correlated when the data is combined? Well, let's look at an example. In the small case, just 2 data points, 212 and 313, only 3 data points for the large case. Within the small category, the 2 points, of course, fall on a line with positive slope, so the correlation is a perfect 1.0. Within the large category, the points are on a different line, again with positive slope, so the correlation is a perfect 1. Taking all 5 points together, online software produces the following. Correlation coefficient negative 0.93, strength and direction very strong negative correlation. Well, yes, I did make up another example with small sample sizes to illustrate the point, but it can happen with larger data sets. The opening graph shows an overall positive correlation despite negative correlations within each of the 5 character sets. And this graph shows the same effect for a much larger data set. So, don't blindly average the averages or correlations. Surprising results can happen. A famous case of Simpson's paradox involves the University of California at Berkeley. The case is nicely discussed at this website. Briefly, in 1973, male applicants to graduate school at Berkeley were accepted at a 44% rate and women at a 35% rate. Did they discriminate against women? Well, at this point, your experience with Simpson's paradox should tell you that an overall average may not reflect averages within categories. Which categories would you like to get the data for? Even if you're not leery of a Simpson's paradox, you might want to know which departments are at fault. So here's the data. Within Department A, women admitted at a much higher rate. Department B, close, but women higher. Department C, close, but men higher. D, also close. E, also close. F, also close. But overall, men were admitted at the 45% rate. Not much evidence of discrimination within a department. So does this clear Berkeley of discrimination? Well, maybe not. Go to the website and read the discussion. Looking at the actual numbers of men and women applicants, what do you see that causes the paradox in this case? Well, over half the men applied to departments A and B, which had the highest acceptance rates. Less than 10% of the women applied to those departments. The lesson should be clear. Before jumping to conclusions based on averages, view the data broken down by category and look at the actual numbers. There are a lot of misleading statements made in the news, and Simpson's paradox opens up doors to distort the facts. Don't be fooled.